Hi everyone. My name is Jongyoon Song from Seoul National University in South Korea. I'm in master course in data science and artificial intelligence laboratory. Thank you for your attending to my presentation. Today, my presentation topic is about customizing the voice of IBM Intu, which is a platform for voice-based artificial intelligence service. This work is a result of collaboration with IBM Korea. This is the outline of today's presentation. First, we present introduction. Recently, we can easily find the services for intelligent personal assistant or artificial intelligence speaker, such as Amazon Echo, Google Home, or Apple Siri. But they have one thing in common, that is, they only provide preset voice options and users should have limited experiences. To improve users' experience, we suggest a voice customization service. The word voice customization means users can freely set the voice of Intu, and it implies that the model should be easy to be trained. And our design requires small speech samples of target speech and no parallel data. Parallel data means a pair of speech uttering the same sentence, which is difficult for users to prepare. The usage flow of voice customization service is as follows. First, users gather speech samples of the voice they prefer. Then, users send the samples to the Intu, and Intu train voice customization module. Then now, users can talk with AI speaker with the customized voice. There are two ways to realize the voice customization service. First is to directly convert text to the speech of preferred voice. However, as the model must map from linguistic feature to acoustic feature, it should have high complexity. As a result, it needs around 30 minutes of speech data of preferred voice to be trained. In contrast, voice conversion model gets the output of TTS model as input, whose voice is before the customization. Next, it converts the speech to the speech of preferred voice. As the input and output have same feature domain, it has lower complexity and requires around 10 minutes of speech data of preferred voice. Considering this fact, we implemented the voice customization service by connecting TTS and voice conversion model. It means that the developers pre-train the TTS model using public speech dataset, and users just train the voice conversion model with around 10 minutes of speech data. Let me explain the overall flow of voice conversion. Source speaker means a speaker of the voice before the conversion, and source speech is a speech of the source speaker. Likewise, target speaker and speech correspond to the after the conversion. Here are some samples of actual voice conversion. This is the source speech.
She turned, fearing that Jock might see what was in her face.
This sample is an actual output our voice conversion model.
She turned, fearing that Jacques might see what was in her face.
As we heard, and this is the voice which users want to customize.
Author of The Danger Trail, Philip Steele, etc.
As we heard, the goal is to achieve a speech where the content is same as that of source speech and the voice is that of target speaker. Here are our main contributions. We suggested voice customization service for machine learning as a service design. And also, we proposed methods for inference time optimization. Finally, we figured out proper amount of target speech to train the voice conversion model. Next is related work. IBM Watson is an API service for cognitive tasks such as conversation, text-to-speech, and language translator. And IBM Intu, Project Intu, is a platform for intelligent personal assistant service using IBM Watson services. As a figure at the bottom, users interact with Intu, and Intu internally calls Watson's API when it needs to perform a cognitive task. There are two kinds of TTS methods. First is unit selection. In this method, when a sentence is given, the model concatenates pieces of real speech from database to complete the output speech. Recently, recurrent neural network (RNN)-based model was adopted. An example for unit selection is IBM Watson's TTS service. The other one is parametric generation method. In this method, the model inferences parameters of acoustic feature and directly generates the output from the acoustic feature. Related convolution neural network and RNN are currently used for this method. DeepMind's WaveNet and Baidu's Deep Voice are the examples for this method. Voice conversion also has a long history. In past, voice conversion started from one-to-one conversion with parallel data. Used model had limitations to reflect the characteristics of the voice. For instance, codebook does discrete mapping between the voices, and Gaussian mixture model assumes some environment and output are blurry. Virtual machine and deep leaf network are not suitable to learn the time dependency of the speech. In recent years, RNN-based model was introduced which can learn time dependency information. Conversion without parallel data was also accomplished. The model we used was suggested by Sun in 2016. It used multi-layer bidirectional RNN, and only target speech was used for training. Therefore, there are no parallel data and alignment issue for the target speech. Next, I will explain our design in detail. It consists of voice conversion network, VCN, and Intu, which includes TTS model. VCN consists of these three stages. The first two stages are training steps. In stage 1, speaker-independent auto-speech recognizer, SIASR, is trained to convert acoustic feature of source speech to linguistic feature. In stage 2, deep bidirectional long short-term memory, LSTM, is trained to convert linguistic feature to acoustic feature of target speech. Stage 3 is inferring step. By connecting SIASR and DBLSTM, whole model can convert acoustic feature of source speech to the acoustic feature of target speech. Then vocoder generates raw wave from the acoustic feature of the target speech. Let's see each stage in detail. SIASR gets male frequency cepstral coefficients, MFCC, as an input. MFCC is an acoustic feature of the speech which represents the energy status of each frequency range. Feature maximum likelihood linear regression, FMLLR, stands for speaker adaptation. Speaker adaptation is to adapt input of voice not in training set. It finds a fine transformation rate W to maximize probabilities of input speech. Output of module is phonetic class posterior probability PPP. It is a kind of linguist feature of the speech. There are phone, triphone, xenon as a phonetic class. Phoneme roughly correspond to each character, but has poor representation. Triphone considers previous and next phonemes, but has too large number of class. So we used xenon as a phonetic class, which clusters similar triphones into one. In summary, SIASR maps MFCC of source speaker to PPP. We use TMIT database to train SIASR on a public speech dataset. At stage 2, DBLSTM is trained to map PPP to acoustic feature of target speaker. DBLSTM is a sort of RNN. It consists of forward and backward directional LSTM, so it can learn time dependency of sequential data robustly. The acoustic feature used here is Merrill-Sefster coefficient MCEP. It is a coefficient of Merrill-Sefster analysis of spectrum of the speech. As SIASR erases source speaker's unique characteristics, target speech can be used as both input and output to train the DBLSTM. Finally, stage 3 assembles SIASR, DBLSTM, and vocoder in order. Fundamental frequency, F0, is the lowest frequency of periodic wave and related with pitch of the speech. And a periodic component is non-periodic features of speech, so it can contain detailed information of the speech. Now, we can finally convert speech of any voice to the speech of target voice. For our experiment, we built a simple echoing model. Intu firstly receives the user's speech through the microphone. Then it extracts text from the speech by using Watson's speech-to-text API. Next, the text is converted to the speech with Intu's voice, and VCN additionally converts Intu's speech to the speech of target voice. Next, we present the experiment and discussion. Considering this structure, we should analyze two issues. One is about additional time consumption by VCN, and the other one is about appropriate size of target speech samples to train VCN. Firstly, we measured elapsed time with respect to each module. As shown in the left graph, we can easily find out that vocoder dominated the elapsed time. And we reorganized experimental result with respect to the class of the task. We can see that feature extraction takes more than a half of the time. Based on this result, we suggest two proposals. First is parallel processing regarding the fact that SIASR and DBLSTM processes are independent of early process of vocoder. Second is extracting the feature of Intu's voice in advance. Because IBM's text-to-speech follows unique selection method, we can store extracted feature of Intu's speech units instead of raw wave of the speech unit. By removing feature extraction processes, we can reduce the inference time dramatically. If two proposals are successfully applied, we can expect to save the time up to 80% of total time of naive model. Next experiment is varying the size of target speech samples. As an indicator of performance, we used Mercedes distortion, MCD. MCD measures MCP distance between reconstructed target speech and original target speech. For reference, here are the speech samples of high MCD and low MCD. This is the sample for high MCD.
You would not keep the truth from me.
And this is the sample for low MCD.
He cried and swung the club wildly.
We performed the MCD measurement on training set and validation set, varying the training set size from 30 to 200. As shown below, when training set size was lower than 100, overfitting circumstance occurred. In other words, if users provide longer than 10 minutes of speech samples, the voice conversion model can be successfully trained with better generalization performance. Finally, we present conclusion. There are conclusions of our study. We confirmed that connecting TTS and VCN suits for voice customization service. Also, we suggested parallel and pre-processing methods for time optimization. Finally, we empirically showed that voice conversion network needs around 10 minutes to be properly trained. I'd like to thank to all the members of our lab, and I'm really thankful to Ishin Choi and Min-Seok Kim, researchers in IBM Korea, for providing the source code of Intu and technical support. And this is the end of my presentation, and thank you for listening. Thank you.
Thank you, Jongyoon. I know you can't hear me, but the others can. So any questions, Jongyoon? And please thank him in the chat. That's where he's looking. He can't hear us, unfortunately. And please thank him in the chat, if you would. Before we end the call, any questions for him? I'll post the recording after the call, maybe today or tomorrow. It'll be on the website, as usual, the CSIG website. Okay, is there a question? Yes, it looks like. Okay, so there is a question for you, Jongyoon. I wonder if you can answer it. For you, Jongyoon. It's rather long. Can you see it? I'll read it out. So somebody called Sama. Sama, could you please introduce yourself in the chat so we know who you are? That would be great. And there's a question from Bob Schloss. Let's see if Jongyoon can answer any of the questions. Speak the answers. Okay, Jongyoon.
Okay.
You can speak, yeah.
Actually, a naive model, it takes around from 50 to 60 seconds, but theoretically, we directly reduce the elapsed time to around 10 seconds, just applying some optimization and to change the structure of IBM Watson's TTS. But if there are more optimization, like hardware, upgrade the hardware specification or other software optimization, we can expect it takes around a few seconds additionally. So if we do more researches, we hope it takes around real-time service can be possible.
Any more questions for Jongyoon before we finish the call? Okay, it looks like there are no more questions from anybody. Okay, so thank you, Jongyoon, and I'm going to end the call. I will end the call. Oh, okay, there is a question. There is a question. Do languages affect the processing? Do you see the question, Jongyoon?
Oh, oh, sorry. As I know, languages have very different number of phonetic class, and the model's complexity should increase as the classes of phonemes increase. So, for example, when the Chinese has more phonetic class, the phoneme classification model should be larger than this model. So it can naturally take a little bit more time to process, but I expect, I guess it is minor difference of time. So if there are sufficient amount of data set to be trained, it will be fine regardless of what language is. Oh, yes, it has side effects because it takes around a very few minutes of samples to train the voice conversion model. And there such as anti-spoofing technology, who discriminates this voice is from the human or the machine. That kind of technology should be improved in parallel to balance the advance of this technology and the security.
Thank you, Jongyoon. I think we're done with the questions now. So I'm going to stop recording.